So this video is not only about shear moment construction in beams, but the principles will be also important in the construction of the shear moment diagrams for frames, as well as the sketching of the elastic curve. So here we go. We have here a beam which is simply supported at its ends and loaded with this arbitrary loading. And we have here the typical shear diagram based from experience. So this is the typical shear diagram, and we have here normally the value of R1 then minus the loading, so there will come a time the shear will be 0, it will be negative, and then closed by the reaction at B. Then the moment diagram also will be 0 at its ends because these are simply supported at their ends and at the ends of the beam, and we have a maximum moment here, and let's locate that maximum moment, which is expected to be at the point where shear is 0. So as we go on, the explanation why the maximum moment occurs at the point where shear is 0 will be clarified or emphasized. So we consider two sections in the beam at distances x1 and x2, and we consider as differential element dx so that the loading over that length dx would be uniform at w, or negative w, because w should be negative. Then the thickness is dx. Let's magnify this segment infinitesimal length of the beam dx, and this is now the beam, and this is the loading, which is rectangular, uniform, negative w dx. And the shear at the left, remember, positive shear at the left section is upward, at the right section positive shear is downward. And for moment, clockwise at the left, counterclockwise at the right. So the shear is denoted by V, and at the right side it will be a certain amount greater or lesser than that of V. That very small difference is denoted by differential V from calculus, so we will call this V plus differential V. And the loading, of course, which acts at the center, and it is negative W dx, and the moment here is M on the right side, counterclockwise, M plus differential M. And we denote this shear value equal to shear 1, and at this point shear sub 2. Both are positive in the figure. Then the difference in shears V2 minus V1 is negative in this case, and it is equal to delta V. Delta V is equal to V2 minus V1. And this is the neutral axis of the beam, and at the end of this neutral axis at the right, where shear plus differential shear passes through, is A. That point, let's denote that by A. So summation forces vertical equals 0. This infinitesimal length of the beam is in equilibrium. So we have V equals V plus dV plus negative W dx. So cancel out V. So therefore dV dx equals W. So remember that this dV dx derivative of shear with respect to x is geometrically interpreted as the slope of the shear curve. This curve here, the shear at any point on this shear curve corresponds to the intensity of the load above. So for instance, at A, the tangent here, the slope of the tangent here is equal to, if this is WA, then WA. At B, the tangent here is equal to WB. So that corresponds to the slope of the shear diagram, which corresponds to the intensity of the load W. Just like in calculus, if you have dy dx, that's the slope of the tangent to the curve between the x and the y coordinates of points. So that's the slope. So dv equals w dx. So this is this tangent line here, red. The slope of this is equal to W, negative W for that case, but W is negative, of course. So dV equals W dx. If we integrate dv with limits from v1 to v2, then that is v2 minus v1, or simply delta v. And the geometric meaning of the right side, w times dx, that's the area of that strip. Therefore, if you evaluate the area of the strip from x1 to x2, therefore that is the area of the load diagram between x1 and x2. So integral of dv from v1 to v2 is equal to integral of the right side of w dx from x1 to x2. So v2 minus v1, which is delta v, is equal to the integral from x1 to x2 of w times dx, which is integral of w dx is the area of this strip here, w dx, and therefore it is the area of the load between x1 and x2. So it is colored blue, so I'll shade the portion of the area on the load diagram which is also blue. So the area of this region shaded with blue is delta V, the difference in shear between the right endpoint and the left endpoint of this region. So likewise, if we extend further, this is M1 and M2. So that's M1, that's M2. The difference, M2 minus M1, is delta M. And delta M is, of course, M2 minus M1. And we sum up moment about A equals 0 of this infinitesimal segment of the beam. So we have V times dx, then plus M, then equals counterclockwise moment, we have M plus dm, then negative W dx times dx over 2. So V plus dv is not involved because it passes through point A. So we can cancel M, and take note that this is differential x, which is a very small quantity, very small quantity, smaller than the smallest thing that you can think of. And you multiply that by another small quantity, same quantity, divided by 2. So from calculus, the product of differentials is 0. So this is negligible. That's almost 0. Then we can cancel out m. Then we have v dx equals dm. Or dm dx is equal to shear. Meaning, derivative of moment with respect to x again is interpreted as the slope of the tangent to the moment curve corresponds to the shear above. So, meaning the slope of the tangent to the moment curve is simply the shear above. So the tangent at this point here at M1 is equal to shear 1, which is positive. The tangent at point M2, which is shear 2, which is lower in positive but lower in magnitude than V1. So that's lower. That's why at this point where shear is 0, the slope is horizontal, because the slope of horizontal line is 0. So that's it. So I hope it's clear. The slope of the tangent to the shear curve corresponds to the intensity of the load above, and the slope of the tangent in the moment curve corresponds to the shear above. So if the shear above, ordinates in the shear above is positive decreasing, then you expect that the slope of the tangents to the moment curve are also, the slopes are also positive decreasing until at this point where the ordinate of the shear diagram is 0. So it is 0, and here we have negative, and the negative slope increases. So that's the interpretation. Same is true here. The slope of the tangent to the shear curve is the intensity of the load, because the intensity of the load is negative, it's downward. So it is negative, and the intensity increases, for example, so it also increases here, and so on and so forth. So that's the interpretation. So integrating dm equals v dx, integrating dm with limits m1 to m2, and the interpretation of the right side is shear times dx, which is the area of this strip in the shear diagram, under the shear diagram. So integral of dm is m2 minus m1, which is delta m, and integral of the right side is simply equal to the area, sum of areas of this strip with limits from x1 to x2. So therefore, it is colored green. So the area or delta M is equal to the area of this shear curve, this one. So again, the change in moment between 2 points on a beam is equal to the area of the shear diagram bounded by those same 2 points. So those are the important concepts on the construction of shear moment diagrams, and I hope that you understand this well so that it's easy for you to construct shear and moment diagrams not only for beams but also for frames. So that's it for this video.